All right, welcome back. So this is our last topic here in Unit 10, the polar form of complex numbers. So we know a complex number uses the special number I, square root of negative 1, to bring into polar format with those special number i's. So first off, we can talk about the absolute value of a complex number. So if your complex number is in the format z equals a plus bi, its absolute value is the square root of a squared plus b squared. Pretty much think Pythagorean theorem. So if I have z equals negative 3 plus 3i, the absolute value of it would be the square root of negative 3 squared plus 3 squared. And we don't use the I is just simply what happens afterwards. The coefficient in front of I, that's the b value, that's what we're using. So we get 9 plus 9, which is 18, and the square root of 18 is 3 root 2. So the absolute value of that particular complex number is just simply 3 root 2. Now, when it comes to the polar form of the complex number itself, z equals a plus bi is the rectangular form. The polar, what's also called the trig form, is z equals r cosine theta plus I sine theta. Meaning, for example, something like this, z equals, let's say, 5 cosine of 2 pi over 3 plus I sine of 2 pi over 3 would be the polar form, the trig form of that complex number. It's always in the format of cosine theta plus I sine theta. I never goes to the cosine. And you can abbreviate this. I've used this myself multiple times in my college classes back in the day, where we abbreviate rather than writing out cosine and sine both times. We just do 5 and then CIS. C for cosine, I goes with sine, and then the angle, since it has to be the same angle there. I'm going to just write out cosine I sine theta each and every time. But if you ever do see 5 cis 2 pi over 3, that's the same thing. The values of a and b and their relationship to r and z and everything else is very similar to when we talked about converting the rectangular polar numbers. You can kind of think of like a and b as x and y. A is equal to r cosine theta, b is r sine theta. R is always the absolute value of z, so that's the square root of a squared plus b squared. Finding theta, theta is the tangent inverse of b over a, where if a happens to be negative, we add pi to it. If a is positive, then we don't. Again, b being negative, kind of like before when y was negative, we don't really care. So if we want to put this into its polar form, we recognize our value of a is our negative 2 root 3, and our value of b is 2. So we have to find r. So r is the square root of negative 2 root 3 squared plus 2 squared. So we get 12 plus 4, which is 16, which is 4. And then we find our theta value. So theta is the tangent inverse of b over a. So 2 over negative 2 root 3. Because a is negative, we add on pi. So this becomes tangent inverse of negative 1 over root 3, which if you recognize that it's immediately, or when you rationalize, you then recognize that negative root 3 over 3, that's going to come from having a pi over 6. And it's going to be a negative pi over 6 because it's negative root 3 over 3. Adding on pi to that gives us 5 pi over 6. So our polar form for this complex number would be z equals r, and then cosine of 5 pi over 6 plus I sine of 5 pi over 6. If you want to use the abbreviation, this would be last time I write it out like this. You'll do 4 cis 5 pi over 6. Both those are perfectly acceptable ways of writing your polar form of the complex number. Now, if it's already in polar form, we want to put it into rectangular form, all we have to do is just use our unit circle knowledge and evaluate the two different trig functions. So cosine of 7 pi over 6 is a negative root 3 over 2, whereas sine of 7 pi over 6 is a 1/2. And then we just distribute the outside number on the inside. 2 times a negative root 3 over 2 is negative root 3. 2 times that should have been a negative 1/2. 2 times a negative 1/2 is a negative 1, so it's negative I. And there's now our rectangular form of the complex number. So as long as you know your unit circle has really been specifying numerous times since we first talked about that way back in Unit 6, you'll be fine. All right, so the next couple things are more formula-driven stuff. So here we're going to talk about the product of two complex numbers. So if I have a complex number z1 and z2, z1, which is defined as r1 cosine theta 1 plus I sine theta 1, z2 being defined as r2 cosine theta 2 plus I sine theta 2, their product, what you do is you do the product of the two r's, r1 and r2, and then for the trig function portion, you're going to add the angles together, theta 1 plus theta 2. So if we have this scenario right here, we're going to be multiplying 5 times 6, which can give us 30. And then the angles, we're going to add 5 pi over 6 with pi over 3, the two different angles in the problem. Obviously, when we're adding angles in its radian format, we're going to need to get common denominators. Pi over 3 is really 2 pi over 6, which gives us 7 pi over 6. So we'd have 30 cosine of 7 pi over 6 plus I sine of 7 pi over 6. And we're leaving it in polar form, so we don't want to evaluate the individual trig functions. We want to leave it as it is in that polar format. So as long as you're careful with the adding of the two angles, really not too bad. The biggest thing really is remembering you're multiplying the numbers, but you're adding the angles themselves. Common mistake would be to multiply the 5 pi over 6 and the pi over 3 because you see you're multiplying. When it comes to division, same idea. We divide the two r's, but now the angles are going to be subtracting. And here you got to make sure you're careful. You're subtracting the correct order. If you're doing r1 over r2, then it's theta 1 minus theta 2. So whatever one's on top is subtracting with whatever one's on the bottom. Don't forget your negative angle identities, because if you get a cosine of negative theta, and it's I sine of negative theta, then you'd rewrite it as cosine positive theta and then minus I sine of positive theta. And if you do end up rewriting it as a minus I sine theta, you can't use the cis abbreviation for this because that's only based on cosine plus sine. So cosine minus sine, we can't use that particular abbreviation anymore. All right, so we have the setup right here. So we have 2 over 3 root 3. So we have our division of the r's, which we need to rationalize then, and get 2 root 3 over 9 is our value in front of everything. And as for the angles, well, we're doing 11 pi over 6. I'm trying to find a space where I can write this in so I can show work. Minus 2 pi over 3, which would be 11 pi over 6 minus 4 pi over 6 for that common denominator, which gives us the theta angle when we're doing top minus bottom is to be 7 pi over 6. So because it's a positive, we don't have to necessarily worry about that negative angle identity stuff. And again, so because we're leaving it as a plus sign there because it's a positive angle, you're welcome if you want to use the cis abbreviation when writing this out. Next up is Dimorov's theorem. This is now talking about when we raise a complex number in polar form to a power. So z is r cosine theta plus I sine theta. We're raising to the power of n. Well, z to the n becomes r to the n, and then the angles are not being raised to the power of n, they're being multiplied by that value of n. So again, like with the multiplication division, we have to be careful with, yes, you're multiplying the r's, but you're adding the angles. Or yes, you're dividing the r's, but you're subtracting the angles. Here, you're raising r to a power, but you're multiplying the angle. So just be careful with the operations you're doing it with. So there's two ways to do this. They're either going to write it out like this, z equals, and find z to the fifth, or they'll literally just put this in like a bracket or parentheses and just put an exponent on the outside. Either way, you're recognizing that we're raising this to the fifth power. So we would have, so our z to the fifth would be 6 to the fifth power, and then cosine of 5 pi over 4 times 5 plus I sine of 5 pi over 4 times 5. Now, depending upon what you're doing with this stuff, you could leave it in the format of 6 to the fifth power. Just kind of depends if they give you you're allowed to use a calculator for the question or not. If you're not, leave it as 6 to the fifth. If you can, 6 to the power of 5 is going to equal 7,776. And then multiplying 5 times 5 pi over 4 is 25 pi over 4. Obviously, if we could have reduced that fraction, we would have to. We can't reduce 25 pi over 4, so we would leave it in that format right there. Our last formula to talk about is the idea of roots of a complex number. So this is for finding all the different distinct roots based on our complex number here. So we have a positive integer n, We have p distinct roots. The way we find this is by doing the p root of r, cosine of theta plus 2 pi n over p, plus I sine of theta plus 2 pi n over p, where n is going to be 0, 1, 2, all the way up to p minus 1. Meaning, so if like p was 4, I want to find 4 distinct roots. I'm going to use n equals 0, 1, 2, and 3. And each of those different n values will give me a different root because it's going to change the angle itself. The outside radical, the p root of p root of r is going to stay the same throughout. It's always cosine, it's always plus I sine. The question is, what's the theta plus 2 pi n over p portion going to be? And again, as n changes, that value itself will change. It will change into a pattern, so we'll be able to recognize what that pattern is as we go through a couple iterations, and that'll make our lives a little bit easier when we calculate out the answer. So here we got p equals 5, so we're going to use n equals 0, 1, 2, 3, and 4 to calculate each of our answers. So we're going to start with the fifth root of 4, and then cosine. Well, our first angle is theta plus 2 pi times 0, because n is 0 to start off with, divided by p, which is 5. So it gives us pi over 3 divided by 5, which is pi over 15. So it's cosine pi over 15 plus I sine of pi over 15. Now the next angle would be next root, would be the fifth root of 4, and then our angle, pi over 3 still, but now it's 2 pi times 1, because the next root is based on n equals 1, the next iteration there. So 2 pi plus pi over 3, 2 pi is really 6 pi over 3, so that's a 7 pi over 3 over 5, which is going to be 7 pi over 15. And then we do our third root here. So again, it's still a fifth root of 4 on the outside. Our angle, pi over 3 plus 2 pi times 2 now, because n equals 2 is the next iteration. 2 pi times 2 is 4 pi. 4 pi is really 12 pi over 3. Add to pi over 3 is 13 pi over 3 over 5, and that gives us 13 pi over 15. And at this point, we can confirm the pattern we recognize after the first two iterations is going to be the correct pattern. We're noticing if we look at pi to 7 pi to 13 pi, the denominator stays at 15, but the numerator is increasing by 6 pi each and every time. Pi, then plus 6 pi is 7 pi, plus 6 pi is 13 pi, so we can follow that logic. The next iteration, for when n is 3, would be cosine of 19 pi over 15, I sine of 19 pi over 15. And then our last iteration, increasing by 6 again, would give us 25 pi over 15 plus I sine of 25 pi over 15. Now, once you've done all your patterns, you need to go back and take a look at them and go, okay, could I reduce any one of those fractions? And pi over 15, 7 pi over 15, 13 pi over 15, 19 pi over 15 all can't be reduced, but that last one can. 25 over 15 is really 5/3, so the proper answer would put 5 pi over 3 in our answer right there. All right, and it's important to make sure that we cut it off once we get to the very end there. If we go one more time, obviously, then we're going to have too much. You should find that the reason why, even though, okay, p is 5, so you think, oh, I need to keep on going until it's 5. Now, we've used 5 values, so the last value of n is always 1 less than the value of p we start off with. But there's still 5 roots because p was 5. All right, so that's it for Unit 10. That's it for our polar functions. We'll deal with this a bit more the next class for calculus, talking about the derivatives and things of that nature. So make sure you're referring back to these videos when you go into that calculus class. Next up is Unit 11, talking about series and sequences. So I'll see everyone next time for that.